Welcome to the 11th episode of Apple Finch Pudding, your gateway into the world of science. I have an amazing treat for you today. Our scientist is no one other than the amazing Lawrence Krauss, author of popular science books such as The Physics of Star Trek, A Universe from Nothing, and The Greatest Story Ever Told. His work as a theoretical physicist focused on elementary particle physics and cosmology, which earned him too many international awards to mention individually. A lot of his time today is used as director of the Origins project and host of the Origins podcast. My co-host for today is Jonas Delva, a close personal friend and an R&D scientist in vaccine research. Welcome, Lawrence and Jonas.
Well, thank you for that lovely and well-crafted introduction. I appreciate it.
I try to keep it as short as possible, but it's hard to keep it short with such a resume.
Well, it's very kind of you. Thanks. Anyway, it's good to be with you virtually here.
Thank you. I'll immediately start with one of my first questions, and that's actually a bit of a silly one, but do you have a favorite science joke or a fun fact or an anecdote or something like that? That's a question for both of you, but I'll start with Lawrence.
I hate it when people ask me for favorite things because, as I often say, I don't think in those terms. I really rarely think hierarchically. There's lots of there's so many fun things that I like about science. But the only sort of science joke that I know, other than most of the jokes I make, I just come up with on the moment, so I forget them right after I've said them. But the only joke that I know originally that is one I've repeated a few times in lecturing, but it's fun anyway, since we're going to talk about maybe cosmology. It involves a speaker like me who's giving a lecture and talking about the fact that in 5 billion years the sun will become a red giant and encompass the Earth, and someone in the audience puts up his hand and says, "Did you say 5 million years?" And the speaker says, "No, 5 billion." And the guy in the audience goes, "Phew, okay."
Close call.
Okay. Anyway.
Oh, that's a great joke. And Jonas, do you have something for us?
Yeah, I was thinking about it, and it's made me remind a fact that I heard in another podcast, No Such Thing as a Fish, about a year ago or something, and they stated that if the area between or the space between the sun and the Earth would be filled with air, we would actually, first of all, see nothing because all the light would be absorbed by this air, but also we would hear the sun, and it would be apparently amazingly loud. And I was quite baffled by that, and I thought it's a perfect fact for this podcast, and I hope now it's not going to get debunked immediately by our scientists. So, when I heard it, it really blew my mind.
That is indeed a fun fact.
Yeah, if it's true, I have to think about it. I can't debunk it without thinking about it more carefully. They both seem like they might be both plausible. The sound thing. Is interesting. I'd have to work out. Well, given the amount of energy that the sun is emitting, 1,300 watts per square meter, I guess, on the Earth. It could. Yeah, I'm not going to debunk them. I'm not going to verify them either, but I haven't thought carefully enough. But it's a possibility.
That's already good enough for me.
Yeah, I can imagine you were stressed about that.
I was a little bit stressed to go in the field of our science.
Don't be stressed. No, that's the last thing I want. Okay.
And my fun fact for today is actually something, Lawrence, you already know it because I actually heard you talk about it with Richard Dawkins.
Oh, okay.
And it's that bats are the only mammals that can fly.
Because flying squirrels are not flying then, right?
Yeah, squirrels are just gliding.
They're floating.
Yeah, we'll talk about that again. Richard and I are doing a public event, which will be a lot of fun. The first time we'll be on stage together in a long time at an Origins project event, November 15th and 16th.
Where is it?
It's going to be in Phoenix. So come on over. And
well, it's a bit of a commute, but
yeah, we'll record it and it'll be online later. But and then the next day I'm going to have an event with 3 Nobel Prize winners actually on cosmology. It's going to be kind of fun on stage as well. It's a beautiful theater, the Orpheum Theater. But Richard and I are going to talk more about his book, Flights of Fancy and other things. So I'll tell him then maybe that it's your favorite fact.
Okay, that would be great. And also, if some of the listeners want to check it out, it will be online. So
yeah, okay, yeah, it'll be online. But I hope some of your listeners, maybe you have such a broad audience that you'll have some people who want to come to to Phoenix, November 15th or 15th. Anyway, okay, that's enough advertising. Let's move on.
Okay.
Enough
Okay.
about that.
Then I'll move to my first science question. And that's actually very closely related to the title of one of your books, A Universe from Nothing. Mm-hmm. So you state that that the universe exists out of nothing, and that we're all a result of quantum nothingness. But what does that mean?
Well, I never say it comes from quantum nothingness. I think the people who talk about my book, especially those who, not yourself, but many of those who like to try and criticize it, and by the way, haven't read the book, say I talk about it coming from quantum nothingness and then argue about what that might be. I don't say that. I try very clearly, I think. I tried very explicitly anyway. I don't know how clear I am in the book to define what I mean by nothing. And that's really important. And I think really one of the key points I wanted to get across in the book is that what we mean by nothing has changed as science has evolved. And that's fine. And some religious people and even some philosophers somehow object to that a definition has to remain the same. But the whole point of science is learning things, and the way we think about things changes. The meaning of universe has changed since the time I began as a scientist. And so one of the important things to recognize, as I point out, is that at least for many versions of nothing, the distinction between nothing and something is not that big. Nothing, is often defined as the absence of something. But as I point out, even empty space is full of boiling, bubbling brew of virtual particles. But there are various versions of nothing, and I go through them pretty carefully. I think. One is empty space, which is really the nothing of the Bible, if you want to think about it. If you read the or various other books, it's sort of a vast void. It's there. Space is, dark and cold and empty or whatever. But that, as I say, is not really nothing. It's full of those virtual particles, and some of those virtual particles can become real particles. They can, empty space can eventually be unstable and produce real particles, given the laws of general relativity and quantum mechanics under the right conditions. But the kind of nothing that's really the most important kind of nothing, which is really the point of the book. Well, the point of the book is really to talk about what we've learned about cosmology. It's not to make some diatribe or promote some dogma. It's just to point out how our picture of the universe has changed dramatically, and in fact allowed us to address that question, which we wouldn't have been able to do when I was starting my career. But the kind of nothing is no space and no time. Literally everything that we experience in our universe, space, time, matter, radiation, all of that did not exist. And then it existed. Okay, so, and then that is allowed given the laws of general relativity and quantum mechanics, at least given as much as we understand them. It's plausible. We don't have a quantum theory of gravity, but it's plausible that space-times can pop into existence spontaneously. And some of them, under certain conditions, can survive 14 billion years, like ours. And that, to me, is the amazing thing that I wanted to demonstrate, that a universe that currently has over 100 billion galaxies, each containing 100 billion stars or more, can pop out of nothing and without any supernatural shenanigans. And it may sound like you're violating energy, and you're not. And that is amazing. Now, did something exist before that? Well, that's an interesting metaphysical question, and one can go into that. And I do discuss sort of a grander version of nothing with no space, no time, no laws, all of that. But those are kind of metaphysical questions. And I hate to say it, but it doesn't really matter for the point of realizing that a whole universe could pop into existence. And we can't even talk about the terms before, right? Because if time begins, then what do you mean by before? And we have to redefine our notions of what we mean by causality and all of that. And that's fine. So, that's what science is about. That's what learning is about, is redefining what we think of common misconceptions or common ideas. So the really interesting version of nothing is no space and no time. And really, our universe didn't exist and then it existed. And people can argue all they want till they're blue in the face about what else that implies. But that I don't really care.
Yeah, and neither should you.
Okay.
But it is mind-boggling, though, to imagine.
It is mind-boggling. That's why I wrote about it. It's amazing. Yeah. I try to take people through it. And the realization and the facts, the scientific discoveries that led us to the realization that if you were going to have a universe that was spontaneously arose from nothing, what would it, and survive 14 billion years, what would it look like? And the remarkable thing is it would look just like the universe in which we live. That doesn't prove that that happened, but it's highly suggestive, I think.
Yeah, no, that's true. And as you mentioned now, and you mentioned also in your book with high precision, we know that the universe is about 13.72 billion years old.
Yeah, maybe maybe I'd like to say between 13.7 and 13.8, even though the experiments give a smaller uncertainty. I think there's still systematic uncertainty somewhere in that range. Yeah,
to be a bit conservative.
Yeah, and I am.
But, okay. Well, my question is actually, how do we know it with such precision? Because it is quite precise, right?
Yeah, what we know it because of the most precise, something that turned cosmology, changed it from an art to a science, was the precise measurement of the cosmic microwave background radiation, which was discovered by accident in New Jersey in 1965 by two people who didn't know what they were doing, but they discovered it anyway.
And how did they do that?
Well, they turned on a radio telescope, a radio receiver, which they turned upward basically. And then, I mean, their contribution was to design a really good one, a receiver, and then try and minimize the amount of noise to try and see what was up there. And they kept getting noise that they couldn't understand. And the noise they couldn't understand, as three remarkable physicists down the road in Princeton told them, was the afterglow of the Big Bang. Because those physicists at Princeton were actually building a telescope to look for that, and realized they'd kind of been scooped, sadly. And they were gentlemen. They didn't have to explain to the guys that they discovered something, but they did. And that was they were remarkable guys. And two of them are deceased, but one of them, Jim Peebles, later on won the Nobel Prize. So I suppose. But anyway, so this discovery that there's this after radiation coming at us, it's now about 3 degrees from all directions, is a prediction of the Big Bang. And it comes, if you want to think, from a surface that was sort of created about 300,000 years after the Big Bang, because as the radiation, which was initially really hot, along with matter, cooled, when the matter was very, very hot, normal matter couldn't exist because protons couldn't capture electrons because the radiation would break them apart. But when the radiation cooled to about 3,000 degrees in temperature, enough hydrogen combined, protons and electrons combined together to form neutral hydrogen, that the universe became transparent to radiation, and that radiation has been traveling throughout the universe unimpeded, more or less, since that time. And so observing that radiation gives us a picture, if you want, of what the universe looked like when it was 300,000 years old. It's a picture, if you wish, of a surface around us, a spherical surface from which the light has been traveling for 13.8 billion years almost. But the nice thing, so that was discovered with a single number in 1965, and that was an important discovery, but it didn't tell us a lot. And it took 25 years or so before finally we had a satellite up in space, because infrared radiation, and I mean the microwave radiation, which is what this is, a lot of it isn't received adequately on Earth, or there's too much, because the Earth is also hot, right? It's much hotter than 3 degrees. So you get up in space and it gives you a better place to look at it. And the Cosmic Background Explorer satellite, which I think was launched in 1989, in 1992 revealed for us, if you wish, an image of that surface by measuring the temperature of the surface and along with high accuracy. The surface is unbelievably smooth. The temperature of the universe is unbelievably uniform, better than 1 part of 10,000. The temperature in that direction is the same as the temperature in that direction. And that is one of the mysteries of the Big Bang, if you wish. But what was really great was this was able to measure temperatures with an accuracy of 1 part in 100,000. And it began to see the small fluctuations in temperature that would later on correspond to galaxies that would, proto-galaxies, lumps of matter that would collapse to form galaxies. So it gave us a picture of that early baby universe, but it did so with an accuracy that allowed us to then begin to turn cosmology into a science, because we could measure things not to a factor of 2, but to 4 or 5 decimal place accuracy. And it was succeeded by a series of other satellites, the the Wilkinson microwave anisotropy probe called WMAP, and then the Planck probe that can measure it ever more accurately. And because of those incredibly accurate measurements, we can now infer the abundance of matter, the total density of protons and neutrons protons and electrons in the universe. And by measuring the temperature so accurately and understanding how the universe evolves and using general relativity, we can work backwards and more or less say how long it took for that radiation to get to its current temperature. And that gives us the age of the universe with that kind of accuracy. We have to use some other modeling that we build in, but based on other observations of galaxies and other things. But when you combine all that astrophysical information, that's what's amazing. We have a standard picture of cosmology now based on this remarkable data that agrees remarkably well. And it agrees remarkably well with a universe that is incredibly strange. It agrees remarkably well with a universe that spatially appears to be flat, three-dimensionally flat. That doesn't mean it's flat like a pancake, but it means that the axes that I make here on Earth somewhere else are all pointing in the same direction, whereas in a curved universe, they would curve as you move from one place to another. And it also corresponds to a universe in which the dominant form of matter is not due to stuff like us, protons and neutrons and electrons, atoms, but is something that doesn't shine and we think is a new type of elementary particle called dark matter. And then the most amazing thing, which a lot of which is my book is about, is the realization that most of the energy in the universe resides in empty space, which is something I'm proud to say I was one of the first people to propose based on the current data. And then the observers discovered it in 1995 to be the case. And so it's all consistent with a very strange universe, which is lovely, because scientists love strange things because it gives them mysteries that they can try and solve. That's a long answer to your question.
But an interesting one.
I hope so.
Does that actually go back to the cosmological constant that Einstein proposed, and that he proposed that to have a static universe, which is not the case because the universe is expanding. And then based on your research, they actually became relevant again. And the inclusion of the dark energy, right?
Well, we don't know what the dark energy is. The dark energy is the energy of empty space, but it seems to coincide extremely well with the cosmological constant, which Einstein put in by fiat, just put in by hand, and the equations in order to solve a problem that wasn't really a problem because the universe wasn't static. And it really didn't even solve the problem, which is really the reason he called it his biggest error. It's not that he introduced it and it wasn't necessary. It turns out it doesn't make the universe static, and he had solved the equations incorrectly. But we now understand that it's quite natural for the universe for this cosmological constant to exist and be non-zero. The big mystery, because of the laws of quantum mechanics and general relativity, but the big mystery is why that number is so small. Because if it was much bigger, as you'd predict from fundamental understanding as we now have it, galaxies wouldn't exist, and neither would stars and neither would us. And the fact that it's so small allows us to exist. And some people have suggested that it's small because we're here to observe it, namely that maybe it could take on any value in different universes, and only in the universes in which it's very small will you have beings like us that can ask the question. It's not a design fact. It's an accident. It's a selection effect, like natural selection and evolution, as I talked about in my book. And that may be the answer. I hope it isn't, because I'd like to be able to predict it from first principles. But that may be just because I'm an old guy and I have to have new kinds of thinking. But the big mystery, we now realize it's basically impossible not to have a cosmological constant according to the laws of physics as we understand it. Why it's so small is the mystery, and that's great to have mysteries, as I say, because it means there's a lot more to discover.
And based on this mass of and energy, so dark matter and dark energy, we have an expanding universe. But can it also collapse back into some kind of big crunch or some sequence of crunch and exploding?
Not if the dark energy remains as it is. That's the other amazing thing. If the dark energy is out there and does correspond to something like a cosmological constant, namely it's a constant value, it doesn't change over time, then once it starts to, it causes the expansion of the universe to actually accelerate once it starts to dominate the energy of the universe. And we measure the universe as accelerating, the expansion is accelerating. That's how it was discovered. But once it takes over, if it doesn't change, it determines the future. And if it continues to dominate, the universe, the expansion of the universe will continue to accelerate forever. And eventually all of the galaxies that we now see will disappear behind the horizon as they move faster, well, relative to us, faster than light away. And the rest of the universe will disappear, as I've written, in about 2 trillion years or so. But we don't know. That's the amazing thing, because we don't know the nature of dark energy. We don't know if that's the case. So we really don't know the future of the universe. But the betting money is that the universe will expand forever at this point. But we'll see.
And do we know at this stage if the universe is infinite? If this expansion can go on forever?
No, we don't know that. Because it's not an operationally answerable question. If the universe were flat, without something called topology, which I won't go into, then it's infinite in size. A flat universe is in general infinite, and it looks like it's flat. So you might say, well, therefore it's infinite. But in fact, if you are in the United States and you go to Kansas and you look out in the plain, the Earth looks flat. In fact, American basketball players seem to think the Earth is flat, and so it's easy to think something's flat because you can't see the curvature. So it could, but it turns out our best ideas about the origin of the universe is that it's really not flat on the largest scales, that it's actually closed. It actually closes on itself, but on a scale so large that in the observable universe, we can't see that curvature. It's flat. But again, if you want to make a universe from nothing, right now, the best way to do it is to do it in a finite size object, if you want to call it that. And a closed universe has zero total energy in general relativity, and that's what you need for a universe to survive, a quantum fluctuation to survive. So if I were to bet, I would say that on scales much bigger than we can see, the universe is actually closed. But the problem is that's hidden behind the horizon, because the universe is expanding so fast, the longer we wait, the less we'll see. And we'll never really get to know that fact. And if inflation really happened in the early universe, then space is, even on the scales that we can't see, is expanding even faster. And so in some sense, it becomes metaphysics. Although the wonderful thing, and I've talked about this more recently, then I think that, more recently I did my book, because the research we did was after that book was written. If we could probe something called gravitational waves from the beginning of time, we might be able to get an indirect bit of evidence that other universes actually exist, which would be wonderful, wouldn't it?
Yeah, that's actually going into the multiverse, right?
Yeah. And right now, the multiverse is a metaphysical construct, which I hate, in the sense of I'm not a big fan of metaphysics, but what's nice is we might be able to turn it into physics by measuring the gravitational waves from the Big Bang, if we can ever measure them. And it's an open question. It's certainly we can't in the near future. The sensitivity is so that you need is better than 1 million times, is more than 1 million times better than the sensitivity we now have. So that's not likely to be the case, but in the near future, but maybe someday, because experimentalists are not stupid people, and they can prove things amazing. Every time I've thought, every time I've underestimated experimentalists, I've discovered I was underestimating them. They did things I never thought would be possible. So I'm just a mere theorist, and so why no?
When you talk about the multiverse, do you have an idea how to imagine that? Do we imagine it like they do in the Marvel movies, like really a separate universe that's close?
Well, I never imagined anything like in the Marvel movies. Thankfully, the universe is far more interesting than science fiction or fantasy. No, the way I imagine the most likely multiverse, and there are different versions of it, is the one that comes from inflation. The theory of inflation tells us that at early times, the universe started to expand very fast due to an energy density in empty space, but that was orders and orders of magnitude bigger than the one we're measuring now. And it was due to some energy that was trapped due to something called a phase transition in particle physics. And that eventually dissipates and it gets released and causes what we now see as the Big Bang. But when the universe is expanding very, very fast, of course, it dilutes everything and becomes empty, but it's expanding very, very fast. And what happens is kind of like snowflakes. There are little seeds here. Here, suddenly the energy is dissipated and you get a Big Bang, boom, and then it starts to expand. But everywhere else, space is expanding very much faster. And then somewhere else, boom, the energy is dissipated and there's a Big Bang. And maybe that Big Bang doesn't survive and it collapses in a big crunch, maybe because the laws of physics are different in each region. So I think of a universe as kind of like a loaf of raisin bread where in the oven, where the loaf is expanding and the raisins are the little universes, except in that case they actually exist beforehand. In this case, they you have to wait till the energy is released, or maybe like snowflakes in a storm. So I think of all these universes as potentially they're universes today coming into existence and other universes that may be collapsing, but the space between them is expanding so fast that of course most of space is the empty space between those universes. And in that picture, which is called internal inflation, that expansion goes on forever. And after an infinite amount of time, you have an infinite number of universes that have been spawned. And people like to talk about that because infinity is a strange thing. And if you have an infinite number of universes, then all sorts of strange things can happen. There could be universes that are more or less identical to our own, where everything that happens in our universe happens, except for me saying the word, it happens. And so in other universes, everything is the same except for that one instant. And every other possibility it happens, and it's weird because once you have infinity, lots of strange things can happen. And people like to write about that stuff. But the more important thing is that if inflation happens, there could be other universes that exist that are being spawned. And it turns out the way that the energy of empty space decays into matter and radiation could be different in each universe and manifest itself as different laws of physics and different forces. So the laws of physics could be different in each universe. We just don't know.
Would it be possible to measure another universe in a sense that you have to probably cross a barrier that we don't know even exists yet?
Well, no, it won't. It isn't possible to measure other universes because they're always separated us by more than the speed by the horizon. So there's no way one universe can impact on any other.
In the book, I read that the universe is flat. Now I heard you talk more about the universe is closed, but how do we imagine those differences as a human being?
We imagine that once again, well, each universe that's spawned in some sense, depending upon the laws of physics, can be a region of a larger universe that has particular properties and could collapse or expand depending upon the nature of the dark energy in that universe. But on the largest scales, of course, what inflation does by blowing up space, just like blowing up a balloon, is even if the original space that comprises what is now all of those multiverses, when that region of space came into existence, it could have been closed, but by blowing it up, it makes it look flatter and flatter and flatter.
So we know the universe itself is expanding, and it's expanding faster and faster, as you said, and at some point it will expand faster than the speed of light.
Yeah. Mm-hmm. Well, different regions of space will be receding faster than the speed of light.
Yeah. Okay. Yeah, you actually explained this in your book, but yeah, Einstein says nothing can move faster than the speed of light.
What Einstein says is that nothing can move through space faster than the speed of light. But space can do whatever it wants in general relativity. Different regions, they're not moving, right? They're not moving in their local surroundings. They're at rest. We're at rest in our local surroundings. But relative to each other, we're receding faster than light. And that's allowed in general relativity. So nothing is moving relative to its local surroundings faster than light. And that's what special relativity tells us is not possible.
And at some point in the far future, we will not be able to see the rest of the universe because it has become so large and nothing can travel to us. Is that more or less correct?
In the far future, galaxies that we currently see will be receding from us faster than light, and the light will never be able to make it to us. So what will happen is they'll appear to be moving. Their redshift will get greater and greater and greater until it becomes infinitely big. We won't, and so they'll just get dimmer and dimmer and dimmer, and eventually not be visible. But eventually, all of the galaxies we now see, except for the ones in our local bound supercluster, will ever be receding from us faster than light, and they'll have disappeared. And in a time scale of order, if the current dark energy remains on its current size, in a time scale of order, a few trillion years.
Now, a bit of a silly question, but one that I heard a few times, that people asking if the solar system could be a giant atom. And my question to you is, why is it not?
Well, a giant atom, I mean, look, all of us have thought of that. Hey, because gravity and electromagnetism look similar in at least classically, 1/r² law, and you got the sun against the and you have the proton and electron. Well, the big difference between an atom and our solar system, one of them is that the atom is behaving quantum mechanically. So the electron isn't like a billiard ball moving around another billiard ball, which is what the original picture of an atom was. It behaves very differently. Whereas on the scale of our solar system, we're very classically behaving. So the Earth tends to look like a big billiard ball, and the sun is and so the dynamics in some sense resemble each other, but and the orbits are classical. They're not really quantized. I mean, on a scale that you could never measure, they might be quantized. But so there's some similarities. But what worries me, I mean, I remember thinking about it when I was a kid. And of course, science fiction stories are written all about that. Whether all of our galaxies could be like in a little marble. Men in Black and all sorts of other things. And certainly I used to be fascinated by that idea. But we shouldn't push analogies too far. And there are certain analogies between a solar system and an atom, but they're not they don't behave the same at all. So, that doesn't say that there can't, that there aren't various very different phenomena happening on different scales in the universe. But our solar system does not behave like a hydrogen atom.
And you also have the twins paradox. So that's when we have a twin and one person leaves on a rocket, for example, near the speed of light. And when he comes back, the person on Earth will be a lot older than the person returning. So time has actually become relative. It's not fixed. But when I tell that to people, they tend not to believe me. And I'm no physicist. So I'm asking you actually, how do you respond to that? Or how would you explain that to people who don't believe it?
One of my favorite sentences is that reality is what was from Philip K. Dick. I said something like, reality is such that it continues to exist even when you stop believing in it. Well, first of all, we can measure it. We can send a plane up around the Earth and have going at speed and come back, and with two atomic clocks, and when it comes back, the two clocks differ. And in fact, we use that every day. In my watch, my phone becomes a GPS device, and the fact that I can use it to get my way to some place I haven't been before is only possible because they're orbiting satellites, and we use that fact that the clocks on those orbiting satellites are traveling are ticking at a different rate than the clocks on Earth. If we didn't, within a second, or within a minute, we'd be a kilometer out. The effects of both special relativity, general relativity are impactful. It turns out I wrote a piece on this, and it's well known now that it's kind of amazing. It's actually, in that case, not special relativity, but general relativity. If we didn't take into account for the fact that clocks are ticking at a different rate on these satellites because they're at a different height above the Earth, in general relativity, that's the case, then they'd be vastly out of sync. So we use that in order to allow GPS to work. So first of all, if you don't believe in it, then don't use a GPS. Don't use it. Okay. But more importantly, what happens is it's a difficult thing to understand. And I remember as an undergraduate trying to grasp it. So the simple thing is that when I'm moving relative to you, my clock is ticking more slowly. Okay. So I'm moving away, and my clock is definitely ticking more slowly relative to you than it is to me. What's strange about special relativity is the same thing is true. If I'm watching your clock, Your clock is ticking more slowly than mine. Okay, so it's reciprocal, and that seems like, how can that be the case? But it's true for both of them. So you might say it's not real. But so if I'm a twin and I'm going and your clock is ticking more slowly than me, okay? What happens? There's a difference if the twin stops and comes back. Then there's a difference between the two twins. One twin on Earth has been at rest, not moving, experiencing no acceleration. But the twin in the spacecraft had to decelerate and then accelerate. And it turns out during that time of deceleration and acceleration, they're not the same, right? One is experiencing a force. And it's during that time that all of the time evolution happens. So the twin is leaving and it comes back to Earth, and it's had 1 year and they're on the spacecraft, and 100 years have transpired on Earth. And what happens is all of that kind of sudden, all of that 100 years of evolution on the Earth happened while this twin is slowing down and speeding up to come back. When he's heading in that direction, the clocks on the Earth are behind him, and when he starts coming back, suddenly the clocks on the Earth are now 100 years ahead of him, that twin paradox really requires you to realize that the twin on the spacecraft is not completely reciprocal. Everything isn't identical. They're not identical observers. Whereas identical observers are ones who are either at rest relative to one another or moving at a constant velocity relative to one another. Because the laws of physics are the same for both of them. There's no extra forces because they're not accelerating. And for them, everything has to be reciprocal, and it is in special relativity. My clock is running slow relative to yours is running slow relative to mine. If you have a ruler, I measure it to be smaller for me than you measure it to be on you. But if I have a ruler, you measure it to be smaller for you rather than relative to me. And so that reciprocity is a central part of special relativity, but it's only true for observers who are either not moving relative to one another or moving at a constant relative speed. The minute you allow for acceleration, that changes, and then you have to go to general relativity. I don't know if that answered for anyone, but certainly the example that we needed for GPS systems should be enough to at least convince people that you can't ignore it.
Yeah, that's true. That's true. And actually, because of biology, I had to think, does size actually matter in that fact, in the sense that when I have to travel 1 meter, it takes me about a second. But when an ant has to travel that same distance, it takes a long time. So in biology, talk about the speed and body lengths per unit of time. Does that matter, for example, if you talk about an atom moving or a planet moving in general relativity?
Well, it matters for an atom because of the fact that the laws of quantum mechanics tell you that on time shorter than you can measure, anything is possible. Right? The atom is doing many different things at the same time, and in fact, on that kind of scales, it's traveling faster than light. It can be traveling faster than light, which makes it would appear to be, if you could measure it, going backwards in time, but you can't measure that. And so because of quantum mechanics, all different motions of the atom are possible between the times you measure it. If what happens on a time scale so short you can't see it happening. That's the Heisenberg uncertainty principle, basically. But as far as an ant or an atom or a planet, the motion of planets around the stars is very slow compared to the speed of light. And so what really matters is the ratio of your speed compared to the speed of light. If your speed is small compared to the speed of light relative to other objects, the effects of relativity are very small. And the effects go as v over c squared. So they're incredibly small for normal motion of walking, or even airplanes, or even satellites, but we just can measure things so precisely we can see those effects. And you have to get motion that's what's called relativistic, that's near the speed of light, for the effects of relativity to be manifest. Okay,
but it doesn't matter if it's a planet or something smaller moving at that speed, as long as the speed is the same.
Yeah. Speed is for relativity. Speed is the ultimate determiner of relative effects. Yeah.
And yeah, now that we're talking on those levels of particles and stuff, like quantum entanglement is something you hear often, but is there a way you can explain it to people who are no physicists?
Well, quantum entanglement says that when it's really just saying that classically we what we see is not what's really happening. And you have to not, and a classical picture is not always a good picture to understand what's happening at a fundamental scale. And quantum entanglement says that if you prepare a quantum mechanical system in a certain state, like particles, like two electrons and an electron, and they're spinning in, say, opposite directions, okay, or they're spinning, and one of them is spinning that way and one of them is spinning that way. When you prepare them in that state, if you separate them, and if they don't interact with any of the outside environment, then they're really not a separate state. They're in one state. Even if they're light years apart, they're in a single quantum mechanical state. And when you measure the quantum mechanical state, you impact on the whole state. So that if I measure this particle and it turns out this particle can be doing many different things at the same time, but we know that together they're in the same, their spins are in opposite direction, but they could be spinning in any different direction, and they are doing all different directions at the same time in quantum mechanics. But suddenly I measure one, boom, I measure it to be here. That means that other one has to be there. And an observer light years away will measure it to be there. And it sounds classically like it's impossible, because instantaneously I'm somehow affecting what a measurement is going to measure over here. But it's not, that's because you're thinking about it incorrectly. They're not separate. They're part of a single quantum mechanical state, and no information is transferred. There's no way an observer over here can know that I made the measurement over here. Because yes, this observer will measure it to be spin down, but big deal. It could have measured it to be spin down if I hadn't measured that particle, right? And if I have 100 particles, it'll measure 50 of them to be spin down and 50 of them to be spin up. But that'll be the same whether I've measured them here or not. So there's no information. There's no communication that can happen faster than light. And so quantum entanglement is fascinating, and we can use it. We will be using it to maybe do everything from help with quantum computers to build protocols that allow us to ensure that there's been no interception of information, so that we can use, you can use it to try and allow quantum cryptography to occur, so that you can encode information in a way that can't be intercepted. There's lots of, if we can do that effectively on large scales for long times, and we don't know if we can do that. But we can use quantum entanglement, and it's fascinating, and it appears to violate all of our notions of what makes sense classically, but that's quantum mechanics, and the world is the way it is. And a lot of people trying to come up with classical pictures that describe it, and whenever they do, the classical picture seems crazy, but that's only because it's, when people talk about the interpretation of quantum mechanics, they're getting it, as we like to say, ass backwards. We're doing it wrong. It should be the interpretation of classical mechanics, because the world is quantum mechanical, and a classical interpretation is only a kludge. It's only an approximation, and of course it's going to sound weird. But the really important thing is to understand that the correct way of understanding it is quantum mechanically, and we can't intuitively picture it because we experience the world on a classical level, and so therefore, it's remarkable that we even discovered quantum mechanics in the first place, and that's why Richard Feynman, who was one of the first people to propose quantum computers, said he hoped that it could do it because they'd be using the laws of quantum mechanics explicitly in order to compute. So maybe they'd understand quantum mechanics better than a human would, and they could explain it to him, even though he understood it pretty well. So anyway, so that quantum entanglement is strange. It's spooky action at a distance, apparently, but that's only because we think about it classically, and what's really happening is quantum mechanical.
When they talk about quantum entanglement, they often talk about photons, and Maxwell described photons as electromagnetic waves.
Mm-hmm.
And could you explain what an electromagnetic wave is and why it was so revolutionary?
Well, yeah, I talk about it a lot in one of my books, as you probably know, in The Greatest Story.
Yeah, sorry.
No, it's okay. Well, Maxwell's based his results on the remarkable experiments of Michael Faraday and others that show that electricity and magnetism are really different manifestations of the same thing. That's remarkable. That's what's remarkable. that one person's magnetism is another person's electricity. They're not different. They're different sides of the same coin. And that is very important. And based on the results of Faraday, what we learn is that if I shake a charge up and down, move a charge up and down, a changing electric field, charge has an electric field around it, will produce a magnetic field. That was a remarkable discovery of Faraday. But we know that a changing magnetic field, and actually this is another result of Faraday, a changing magnetic field will produce an electric field. So a changing electric field produces this magnetic field around it, but if it's constantly changing, the magnetic field is constantly changing. But if the magnetic field is constantly changing, then it's producing a changing electric field, which is producing a changing magnetic field. And what Maxwell showed is there'd be a disturbance. If I shake a charge, there'll be a disturbance in fields that will propagate out, and he calculated the speed. And lo and behold, the speed of that disturbance was what was measured to be the speed of light, demonstrating that light was an electromagnetic wave. And that's wonderful. Except we also know that, and this is where quantum mechanics comes in, that electromagnetic wave that we see, it can, if it's very weak, it turns out when you try and measure it, you see individual clicks as if separate particles are coming through. And so that's this wave particle duality, that wave actually, a large scale wave is actually a coherent superposition of many quantum objects called photons, which if you can isolate one behaves like a single particle. And that weirdness persists, because again, if you take individual particles and you send them out, they'll behave like particles or if you don't measure them and you send many of them out, they'll behave like waves. And what you see at either end will be depend on the measurements you make. And that's one of the weird things of quantum mechanics, a double slit experiment. But Maxwell's beautiful theory was a unification of electricity and magnetism. The first theory that showed that they're really different manifestations of the same thing. And it created a kind of example that we continue to exploit with now in physics, which is realizing that things that appear to be different can be the same, different manifestations, same thing. And maybe all of the four forces in nature, electricity and magnetism seem like two different forces, but they're the same. We've now learned that electricity and magnetism and the so-called weak force, which governs the nuclear reactions that power the sun, are really also different manifestations of the same thing. And that was another great part of the greatest story ever told so far. That was the realization in the 1960s and 70s that we now have an electroweak theory, that electromagnetism is and the weak interaction are tied together in some ways in a single theory. And then there's four forces of nature. Maybe they're all tied together and we don't know yet. And we think that perhaps they could be. And we're trying to search for ways to unify them. But it was Maxwell's theory was the first step on a wonderful road that has led to what's called the standard model of particle physics nowadays.
And before reading your book, I have never heard of this, but there are virtual particles. Can you explain what those are and why they are so special?
Well, they're special because they're virtual. Namely, you can't see them. Namely, they exist on any region of space. Because of quantum mechanics, all sorts of weird stuff can be happening. I like to say it's like the White House or corporate America. If you can't see it, anything goes. And so on time scales that are so short that you can't measure them, strange things can be happening. And I told you, it means if you measure the motion of an individual particle, for example, if you didn't measure it on the time scale so short you can't measure it, it could suddenly be moving faster than light and then slow down. During that time, things that are moving faster than light would be going backwards in time. So if I wanted to draw the trajectory of a particle in time, it'd be going forward, then backward, then forward. But then let's look at a time slice. Back here I have one particle. But then at some intermediate time, I have a particle, another particle going backwards in time, and another particle going forwards in time, all at the same time slice. So suddenly it looks like I have three particles. Well, that particle going backwards in time, we can think of as an antiparticle going forwards in time. And therefore, what it really looks like, and this is Feynman's picture, is a particle going forwards in time. Suddenly, out of nothing, a particle-antiparticle pair propagate out, that antiparticle annihilates the first particle, and then later on you just have one particle again. And so in the intermediate time, you suddenly had a particle-antiparticle pair that appeared and then disappeared. Those are virtual particles. Now, it sounds like, okay, big deal. That's like counting angels on the head of a pin. But it turns out those virtual particle-antiparticle pairs, which exist for short times, can affect the properties of atoms. And we can calculate the effects. And this is one of the things that Feynman did. We can calculate the effects, and the effects are exactly what we measure. It allows us to calculate the spectrum of atoms to 12 decimal place accuracy or better. And if we didn't include the virtual particles, we'd get the wrong answer. So we know they're there even though you can't measure them. And it means that empty space is much more interesting. Inside of a proton, there are all sorts of strange things happening. It turns out if you add up the mass of the quarks inside of a proton, their mass is much less than the mass of the proton. But it's due to the effects of all the virtual particles and fields that are popping in and out of existence that give mass to the proton. So they allow us to exist. So if it weren't for the virtual particles and fields, protons wouldn't be so massive and we wouldn't be around. And so these virtual particles are virtual. Empty space is empty. If you try and look in there, there's nothing there. But in fact, we know a lot of stuff is happening. And that's what I mean. Nothing and something are not so different. To make full circle back to your first question. And since we're near the end, it's good to go for circle.
Yeah, that's true. Do you have time for a few more questions or not really?
Maybe one more question if it's really good.
One would be, what does being a good scientist mean to you?
Well, I mean, being a good scientist means you think like a scientist and you try and question your assumptions, and you base your ideas on experiments, which you then test over and over again. So it means using the scientific method and the scientific process in everything you do, and also being willing to change your mind, be wrong. Let nature be what determines reality, and not what you like it to be. And also recognizing that the imagination of nature exceeds the imagination of human beings, and therefore be willing to be surprised and enjoy that surprising. So being happy to not understand things, and recognize that there are things one doesn't understand, and being excited about the possibility of trying to learn about how to understand them. All of that's involved being a good scientist, I think.
It's a very cool way of saying it.
And if you have one take-home message for our listeners, what would it be?
I don't like to give advice, but the only advice I ever give is don't let the bastards get you down. Namely, there'll be times in life where you'll be challenged, and people around you may make you feel like garbage, or may make you feel wrong. And it's important to listen to others, but ultimately just keep plugging away and be willing to change your mind. But as Richard Feynman says, don't worry about what other people think so much. That doesn't mean disregard their feelings. I don't mean that. I mean, ultimately, just remember why you're excited about what you're doing and keep plugging away at it. And be prepared for it to lead somewhere that you never expected it to lead. And that's the beauty and adventure that is life.
Thank you very much. This was the 11th episode of Apple Finch Pudding. I want to thank Lawrence Krauss for the information and Jonas Delva for the additional questions. Let's meet again for the next episode of Apple Finch Pudding.